Hello, this video shows processing of a Wingtra Hesai XT-32M2X drone LiDAR data using Wizard in TerraScan, TerraMatch and TerraModeler. I start with Wizard new drone project and I select the type of a scanner system. As an input, I specify one or multiple point cloud files, most often LAS files. Our input file is substantial size, 34 gigabytes in size. I give a name to my project. The input file did not have a projection system information in it. So I tell the software what is the projection system of the input data. I can see that the input coordinates of the first point, easting is 449,000, northing is 5.2 million. In addition to a point cloud file, I need to have one or multiple trajectory files. And we have a dataset which has two trajectories, that is 2 flight sessions, but all the points are coming in as one LAS file. And I specify the projection system in which I want to work in, and I specify that I'm going to use ellipsoidal elevations, and I click OK. So this will read the point cloud file in, and it will remove duplicate points. So in some places there's identical X, Y, Z points in the input data, and we only keep one point in such cases. And this will also read in the trajectory solution, apply the coordinate transformation from longitude latitude to our desired projection system, and it will do a time conversion so that the point cloud and the trajectory information will have the same timestamps. And this screen recording is going to be shorter than the actual time spent on the steps. So whenever there's a long processing step, I will remove the waiting time from the screen recording. So in reality things take a longer time than what our screen recording shows. So I now have the point cloud and the trajectory solution loaded. Usually I want to get familiar with a point cloud when I first see it. So we have quite a lot of forest. The terrain doesn't look so demanding. We have some power line wires. We have a few buildings here. And it's a good idea to take a look at, do we have a lot of noise in the air or noise below the ground? And it doesn't look like we have a lot of noise in the air, a lot of noise below the ground. But there are some points way below the ground. And so we do have some noise, but not so much of a problem. I will check the point density. We have 158 points per square meter. Trajectory solutions were brought in. This is the first flight session, and this is the second flight session. And now I would start with the processing steps. I can run processing steps automatically, but for the purposes of showing what each step does, for you to understand the processing steps, I'm going to do this one step at a time to explain what is happening. Splitting trajectories gives us individual passes over the site. And it assigns line numbers to the point cloud, which then means that I can look at line coloring. So now I can take cross sections from the dataset to view how well or how badly flight lines match each other. And here I see that the blue flight path, the point cloud, is a little lower than the green or the white one. So there is potentially a benefit from running match passes, something which matches flight passes to each other. And here the same, that the blue is a little lower than the green one. The next optional step in the processing wizard workflow is matching passes. The mismatches are not so big, so I can specify a slightly smaller maximum mismatch, and I decide that I will do heading roll pitch per session, and I will do heading roll and elevation per line. And I'm not seeing mirror angle effect, a sad face, smiling face effect. So I don't think I need to solve and correct for mirror angle correction. Match passes step in the wizard calls TerraMatch. So you also need to have a TerraMatch license to be able to do the match passes. And match passes will first of all classify temporarily the points suitable for matching surfaces from different flight passes with each other. And then it will collect tie line observations of the mismatches, of the differences between laser data from different flight passes. And these observations of differences or tie lines, the software can use to derive corrections. And practically always with airborne data, we do want to solve and correct for heading roll pitch per flight session, a systematic bias in our trajectory solution, a small heading correction, small roll correction, small pitch correction to apply to the data. And then depending on the system, I may choose additional levels of corrections to apply. In this case, I chose to do heading, roll, and elevation per line. Elevation per line is easy to explain. It means that the software will lower one flight line data by 2 centimeters and raise another flight line data by 1 centimeter, and so on. So now the matching is done, and now the blue flight path is matching the other ones better in both cross sections. And in the report, I want to look at what happens to the mismatch values. My starting average mismatch is 22 millimeters. Heading, roll, pitch correction per session with these values in here reduces the mismatch in elevation in the tie line observations to an average value of 18 millimeters. The second round of correction, the solution per line, takes us from 18 millimeters to 13 millimeters. The biggest elevation shifts we have here are close to 9 centimeters. My next step in the processing wizard is cutting overlap. At the moment we have 481 million points. Cut overlap takes out the overlapping data from different flight paths, keeping only one flight path data at one object, one location. And it always keeps the shorter measurement data. So whatever flight path sees an object or a spot on the ground or a building roof surface, whatever path sees that at the shortest distance, that's the data which is going to be kept. And when we remove longer distance measurements, we are taking out less accurate data. The shorter measurement, the points in the central part of the scan corridor, those are more accurate in positioning. And cutting overlap also reduces the data volume. Our dataset becomes smaller, easier to handle, and more uniform point density. So when cut overlap is done, we have reduced the dataset from 481 million to 330 million. And we have only one flight path data at one spot. If a more distant flight path sees something for which there's no points from the closest flight path, then that is kept. My next step in the processing workflow is smoothing. We do have some point-to-point noise which smoothen surfaces and remove noise around surface will smoothen. And I showed you in the beginning that there are some points below the ground. Classify isolated points and classify nose below ground are for removing noise data in the point cloud. The smoothing is an operation which modifies the X, Y, Z of each point. If it looks like there is a local surface and a small change to the X, Y, Z of the point can make the point match the local fitted second degree surface nicer. We should see the effect of smoothing in the cross sections view windows. The cross sections will become cleaner lines, the image of the point cloud in the cross section. So now the smoothing is done. The laser data looks cleaner in a cross section on a hard surface. And some points have been classified as low points. So now the point or the points in here are in class 7, low point class. And some of the points have been classified into class called noise. And let's see if I can find an example of noise class. So now the colored points are classified as noise. They do not match the local surface so well. And often I would keep the noise class points out of classes such as building roof or ground surface, or anything that I believe to be a more noiseless, cleaner surface. The next step in the wizard is thinning points to inactive. And this is for speed. So this is not a mandatory step to do. And I choose here a little bit bigger spacing. The default value of 0.1. That is the default for drone data, which is often a little higher density data sets. And here I go to a little lower density of active points to be kept. So in the beginning we had 158 points per square meter. Cutting overlap removed about 1/3. So we have now about 100 points per square meter. And we don't need every point to decide what is ground, what is tree, what is building roof. We can speed later steps by moving some of the points to an inactive class. And the inactive class we will classify at the very end of the process by copying the classification from the closest actively classified point. So thinning is done. And now many of the points have been moved to inactive class. And now the visible points in class in window 2 are the ones that I would actively use to make classification decisions. And in view number 1 I will switch the eliminated from active classification, points eliminated off, and look at intensity coloring or elevation coloring. So these are the points that will be actively used to decide what is ground, what is building roof, what is tree. The next step in the wizard is classifying ground. And after that comes checking ground. Ground is normally an important end product, and I would always want to do some user inspection of the ground classification to verify that the ground classification is good. That check ground step in the wizard is the one step which cannot be done automatically. But for most datasets, it is okay to do checking of the ground at the very end, to run all the wizard steps first and then do the operator work checking the ground visually, doing that at the end of the process. In this demo I will do the check ground right after classifying ground. So the ground classification has classified some of the points into class 2. So in elevation coloring, my ground looks like this, whereas all the points look like this. And in a cross section, our ground classification looks like this. And ground, as I said, is pretty much always an important end product. I do want to take some time to view the ground classification result. So I started a tool in TerraScan, create editable model, which calls TerraModeler. So now I'm going to be using functionality from TerraModeler as well. And there is now a triangulated model in TerraModeler of the points classified as ground. And I can view the shaded surface as a display and look for anything that doesn't look right. So anything that catches my eye, I may want to check to make the decision if the classification is good or if this feature should be excluded from the ground. Where I have man-made buildings, I'm more likely to have complexity in our ground. And we often have entrances to basement levels of buildings. And if I want to have those removed from the ground, then I would do classification. And as I do classification, the shaded surface is updated. So the editable model is something which is hot linked to the classification of the point cloud. if I use manual classification tools to classify something, it will be automatically reflected in the shaded surface. And in this way I keep looking for anything that doesn't look right. And in the man-made environment there is a lot of complexity, a lot of holes, a lot of entrances to basements and so on. And so these are real features, but they don't necessarily belong in the ground model. And I would keep doing this work as long as I see something that I want to fix in the ground classification. The natural terrain is easier, and I don't have much to do in the natural terrain. It is the entrances to the basements, the manholes and other objects in the built up environment where I have more things to do. In this demo I'm not going to spend more time on the ground. I decide that now it's good enough for the purposes of the demo. I have shown the workflow, the tools that need to be used to improve the ground classification. When I'm happy with the ground, the first thing I would perhaps do is get rid of the triangulated model. So I don't need that consuming memory. And then I would classify above ground features. And now I will do rest of the 4 steps in one go. Before doing it, I'll just explain what the 4 steps do. First step, classify height from ground, classifies points into low, medium and high vegetation based on height from ground. And that's my initial separation of the above ground points. Low vegetation I don't do anything further with, but anything which is more than 25 centimeters above ground, that's a user setting, goes into medium or high vegetation, and those I will classify further through segmentation or grouping into 8 different point classes: building roof, roof structure, wall, tree, vegetation, car and pole. And that step classify above ground features. The next step is copy result to inactive points. About half of the points were placed into inactive class with the idea of speeding processes up. And this step will copy classification result to the inactive points for the above ground features. And then copy result to noise points will assign classes to those points classified as noise where there is a vegetation or tree class point close by. And I will click OK. And this is the most time consuming phase of the demo. So classifying the above ground features takes the longest time in this whole process. So the classification of above ground features has classified points into classes: building roof, vegetation, roof structure, wall structure, tree, car and pole. Red points are classified as building roof. And then there's associated classes: roof structure, wall structure. Roof structure, which is the white points, there's something which is on a building roof but not big enough planar surface to be classified as a main planar roof surface. And wall structure is something next to a building roof. It can be vegetation, or often it is some man-made structures. In this dataset, a lot of points become 3. And the trees, like everything that was above ground features, has been grouped. And grouping gives the software the understanding of what points belong to one tree, which points form one tree. And that is the basis for the ability to do a list of trees. And we have a big number of points also in vegetation class. Which is points which do not rise, or the group does not reach enough height from the ground, so it's not tall enough to be considered a tree. And the vegetation is then also pretty much our class for things that are not recognized as being something else. So it can have some man-made features in it as well. And this is my complete classification. So the automatic classification steps have been completed, and now it would be a good time to save the points. And I can decide on the file format in which to save. Maybe I'll do a fast binary, and I'll simply call this result.fbi. Thank you for watching.